evening, Prof. Rose. Okay, the meeting is being recorded. Okay, so this morning we are very happy that we have a Prof. Karen Rose to give us a very exciting presentation. So I first give a brief introduction of Prof. Rose, just in case you don't know her. Prof. Rose has been a professor at MIT since 1997. So currently, she is the associate head of the Department of Materials Science and Engineering. She graduated from Cambridge with both bachelor degrees and PhD degrees. And she's currently the fellow of EPS, the MRS, the UK Institute of Physics, and the IEEE. And he was also the chair of the 2011 Magnetism and Magnetic Material Conferences. Prof. Rose's research is directly towards magnetic properties of thin films and small structures. So her talk today is magnetic insulators for spintronics, photonics, and magnetoelectric devices. So now I think let's welcome Prof. Rose, and now the stage is yours. Thank you very much for giving us this talk.
Well, thank you, Professor Wang. It's a pleasure to be here, and I'm vicariously enjoying the nice weather over in Singapore from here in Boston. So I'm a material scientist, and I'm going to show you some work that we've been doing in recent years on magnetic insulators. So this is very much from the point of view of designing materials which have specific magnetic properties for various device applications. I want to start by acknowledging a number of other groups I've worked with, particularly Professor Beach and Professor Liu, who also work in spintronics, and then a couple of other faculty in material science and engineering, Professor Yildiz and Professor Lebeau, and then a large collection of students and postdocs who've contributed to this work. Okay, so I'm going to first of all motivate this work by explaining that complex oxides, there are many kinds of complex oxides, and they have a lot of very desirable properties. Most of the time one thinks of Perovskites as a complex oxide, but there are others like spinels and garnets, and I'm actually going to talk mainly about garnets for about the first 2/3 of this seminar. And in all of these materials, there's a very wide range of properties that one can engineer through the strain, the composition, the substrate, interfacial effects, and so on. And they have a lot of very useful and interesting properties like ferroelectricity, magnetism, superconductivity, and so forth. All of these properties make them useful in devices. And if you look at this schematic down the bottom from a review article, the devices can use a number of state variables, and those are manifested in a number of materials, of which complex oxides is an important part. From those state variables, one can develop devices and then ultimately architectures to do functions like memory or computation. So we're very interested in the technological properties of these kinds of materials. Now, they're challenging materials to deal with, and the primary reason they're challenging is because they are usually grown at high temperatures, and there are a lot of possible materials that can form with a given set of ingredients. And that means that we have to be able to select the phase, the structure, the composition that we want in order to get the properties that we want. Okay, so what I'm going to cover in this seminar is some spintronic properties of materials, particularly garnets with rare earths and bismuth. And then I want to talk about some photonic materials, which are also garnets, and these are useful in integrated photonic circuits. And then finally, I'll talk about magnetoelectrics, which are materials where we have both magnetism and ferroelectricity in the same material. And that means that we can do electrical control of magnetism. So I want to show you some materials developments on that. Let's start with some comments about growing these materials. We use pulsed laser deposition, where you start with a target of the material, that's a sintered ceramic in our case, and we hit it with a laser. So the laser is a pulsed laser. It's a ultraviolet laser, 248 nanometer laser. It hits the target, and that creates a plume of evaporated material which lands on a heated substrate. And we can add oxygen or other gases into the chamber, or it can be done in vacuum. PLD is a very adaptable process. It's very easy to change targets or to do combinatorial growth, where we have multiple targets in the chamber at once and we move from one to the other. So it makes it very good and flexible for research. It's not so easy for manufacturing because the area of the plasma plume is quite small. So for manufacturing, we tend to use sputter deposition or other kinds of processes like liquid phase epitaxy or atomic layer deposition. And in general, one can translate the processes that we develop with PLD into other modes of making the material. Now, we can make single crystal films like the one shown up here. This is a YIG, yttrium iron garnet, on top of a garnet substrate. So we can make single crystal films using epitaxial growth. We can also make polycrystalline films by growing on top of a non-epitaxial matched substrate, like an amorphous layer of silica or silicon nitride, or some material that doesn't have a lattice match with the material we're trying to grow. And although I'm not going to talk about it here, we can also make freestanding films. And this is actually a freestanding sheet of YIG, about 100 nanometers thick, which is made by an exfoliation process on a garnet substrate and then peeled off. I want to talk about garnets first. So let me introduce you to the garnet structure. Garnet is a ferrimagnetic insulator, and I'll explain more about how the ferrimagnetism works in garnet. But the prototypical garnet is YIG, yttrium iron oxide, and this has some wonderful properties. It's a very good insulator, so there's no current flow, no ohmic losses. And it also has very low magnetic damping, which means that if we have a magnetic excitation like a spin wave propagating through the YIG, it doesn't get attenuated very much. So we can get long-range propagation of spin waves, and we can also get very fast dynamics. So those are very appealing from the device point of view. The crystal structure, however, is very complex. And what you're looking at here in this image is actually one unit cell. So the unit cell contains 160 atoms, and it is cubic, and it has a lattice parameter of about 1.2 nanometers. So these are truly complex oxides, much more so than perovskites, and making sure that one gets the stable phase as the garnet is not always possible. So we resort to epitaxy to stabilize compositions that would not form a garnet in bulk. Let's look at the magnetic structure. There are tetrahedral sites and octahedral sites, which both contain iron. So you can see here the octahedral sites are blue and the tetrahedral ones are green. And inside each of those is an iron 3+ ion. And they're coupled anti-parallel. So that gives a net magnetization of 5 Bohr magnetons per formula unit, because the yttrium is not a magnetic ion. Now, if we replace yttrium with something magnetic like a rare earth, or we can put in there bismuth and cerium, we can change the properties quite dramatically. So these garnets actually have the same structure as natural garnet. And if you look at the formulas for natural garnet, there's a range of different garnets which have different colors, but these are silicates. And in the iron garnet structure, the silicon and this site here are the octahedral and tetrahedral sites, which are filled up with iron. Iron garnet has a lot of applications. YIG itself was developed as a very low loss material for radio frequency applications. And one can use it for devices like an antenna, dielectric antenna. where the incoming RF excites a spin wave in the garnet, which can be detected. They can also be used for filters, and that's using resonance of the garnet. And of course, bubble memories, which is a very old technology now from the 70s, used garnet films to store information. There are also magneto-optical isolators, which I will talk about later on. And in these materials, we use the magneto-optical behavior, the Faraday effect of these materials, to give us optical isolation in the near infrared and visible wavelengths. In the device point of view, thin film point of view, the garnets have a lot of functionality, which enables a wide range of behavior and properties and devices to be made. So we can use phenomena like spin Hall effects, where we take the garnet and we put a layer of heavy metal on top of it. And then when a charge current flows through the heavy metal, it produces a spin current, which can be injected into the garnet. And I'll talk about that more later on. So we can use spin Hall effect to actually detect and to manipulate the magnetization of a garnet film, or actually any other magnetic insulator for that matter. We can, as I've mentioned, use garnets for spin wave devices, where we have long range propagation of spin waves, and or magnons, if you prefer. And these spin waves or magnons can be emitted by an antenna, a coplanar waveguide here, and detected by another coplanar waveguide. And that allows for devices that use interference of spin waves to process information. We can also use the optical properties of garnets to make magneto-optical devices integrated on chip. And this is a cross-section through a garnet-clad silicon waveguide, which performs the function of an optical isolator. So with all these interesting properties, we can make spintronic devices, magnonic devices, and also photonic devices out of garnets. When we grow garnets on substrates, like the GGG I mentioned earlier, which is a non-magnetic garnet substrate, we get very good quality films. This is showing a thulium iron garnet, rare earth iron garnet film. That's this top bit on top of a substrate, which is underneath, under the dotted yellow line. And you really can't see the interface unless you do some chemical mapping. It's a very perfect interface, and there are no dislocations or other obvious defects. So unlike simpler materials, the Burger's vector of a dislocation in a garnet would be very large, and that makes them very energetic. So we don't typically find dislocations in these films. One can sometimes find partial dislocations, but these films maintain a strain which is determined by the substrate. So we grow films with a significant lattice strain. If we look at the composition, we can see a sharp interface. The interface diffuseness is on the order of 1 nanometer, so 1 unit cell, and that represents the interdiffusion during the growth process. So these are very high quality materials when they're grown epitaxially. Let's look at how we can engineer their magnetic properties then. If we recall that the garnet has 2 sites for iron, octahedral and tetrahedral, those are coupled anti-parallel. If there's a magnetic ion on the dodecahedral site, then that couples also parallel to the octahedral site. So we have actually 3 sublattices in this material. And we can use a molecular field model to calculate, for example, the magnetization as a function of temperature. And we often find that for these garnets with rare earth ions, particularly those rare earths near the middle of the row on the periodic table, we can get a compensation temperature where the magnetization goes to 0. And that's where the octahedral ion plus the dodecahedral ion has an equal moment to the tetrahedral ion. So at that temperature, the material has no net magnetization. And we can calculate how that temperature varies with composition of the material. So clearly, by changing the composition of the rare earth And also by substituting on the ion sites, we can create a range of different magnetic properties. Let's look at some of the materials we can make. These three at the top are thulium garnet. This is dysprosium garnet, bismuth yttrium garnet, terbium garnet, and terbium scandium garnet. So in each of these materials, we've grown a thin film using pulsed laser deposition, and we can see a range of properties. They have different coercivities, different magnetizations. And looking at the data for bulk garnets, one can identify a range of different M versus T behavior, which is expected from the bulk material. It's often advantageous in these thin films to have the magnetization pointing out of plane, and I will come back to that. We can engineer this as well by the choice of the material and the substrate, and all of these examples I'm showing you actually have an out of plane easy axis. Let's look now at how we can engineer the site occupancy or understand the site occupancy of these materials to relate to their magnetic properties. We had a long-standing mystery as my students grew films of terbium garnet, terbium ion garnet here. So terbium 3 ion 5012. It's supposed to behave like this black line in bulk, have a magnetization that drops to 0 at about 240 Kelvin. That's the compensation temperature, and then comes up again and then goes down to the Curie temperature, which is 550 Kelvin. But instead, when we made our thin films, we found that the compensation temperature was too high. It was actually above room temperature, and the Curie temperature was too low. It was down around 485 Kelvin. So what's going on here was the big outstanding mystery. And we spent a lot of time analyzing this, and we found that these materials, first of all, they have some excess terbium. That ratio, terbium to iron, should be 3 to 5. And it's actually 0.86 in these materials. And we found by X-ray photoemission spectroscopy that we had both 3+ and 4+ terbium. So the 4+ doesn't belong there. These are all supposed to be trivalent. So if we go through and finish this analysis, we can actually work out that the off stoichiometry of this material and the presence of the wrong kind of valence states is actually responsible for the behavior that we see. So the non-bulk site occupancy is what's causing the material to behave differently from the bulk. So rather than seeing this as a disadvantage, we see it as another way of engineering the behavior of the material to get exactly what we want, whether that's Curie temperature, compensation temperature, or net magnetization. We can see this to a greater extreme if we make material with a massive off stoichiometry. So we made YIG with yttrium to iron, instead of being 3 to 5, being 1 to 1. And yet it still forms as a garnet, and its formula looks like this: Y3 YFE4012 as a garnet. And the yttrium is sitting on mainly on the octahedral sites, being non-magnetic. And this explains the lower Curie temperature and the higher low temperature magnetization of this kind of material. So the take-home message of this is that even though in bulk, these kind of garnets will not tolerate an off stoichiometry. So if I grew this material Y2Fe equals 1 to 1 in bulk, I would actually form a perovskite, YFE03. But instead, being stabilized by epitaxial growth, we can get a garnet structure with a very non-ideal composition. And that means that we have a way of creating materials which are far away from the bulk properties. Let's look now at the anisotropy of these materials. I mentioned earlier that it's very advantageous to get perpendicular magnetic anisotropy. And when we go on to current-induced switching in these films, I'll show you why that is. But the question is, how do we get PMA? Perpendicular anisotropy. That means that the magnetization needs to point out of the film plane. Typically, we would get it by magnetostriction or magnetoelastic anisotropy, where we arrange for the film to have a certain strain state and a certain magnetostriction coefficient. For example, if a material has a negative magnetostriction and in plane tension, then it's going to drive it towards having perpendicular anisotropy. And conversely, a positive magnetostriction and an in-plane compression will give us perpendicular anisotropy. And we can see those in two examples: thulium garnet on a GGG substrate, that's the gadolinium gallium garnet, or europium garnet on GGG. Both of these have PMA, and you can see them here. The red one's the europium and the blue one is the thulium. But what happens in between? This is a mixture europium thulium garnet. And if we look at its X-ray peak, there's no strain at all. This film actually has a good lattice match to the substrate. So there's no way that magnetostriction could be giving us that perpendicular anisotropy. And it turns out that there's evidence for an additional form of anisotropy due to growth, which is because the rare earth ions actually arrange themselves preferentially into the lattice sites. So we get a kind of additional anisotropy from the material. It's no longer really cubic. And that can be very strong for these mixed compositions. So this gives us a perpendicular anisotropy, which is independent of strain. Because of the perpendicular anisotropy, we can get really pretty looking domain patterns. And I'm showing this movie. I hope it's playing on your screens, but this is one of these perpendicular films. This is actually thulium garnet, and an applied field of just a few oersteds will cause these domains to expand and contract. You can see them nucleating along a scratch and then expanding outwards. So this is one of the consequences of having that perpendicular anisotropy. Okay, let's look now at the interface of garnet heterostructures. Typically, one would grow the garnet in the PLD chamber and then take it out of that chamber. Maybe you do something to it, pattern it, or leave it sitting in the lab, and then finally grow something else on top, like platinum. And if we do that, there's a layer of contaminant, this dark layer in between, which is deleterious to the transport of spin between the platinum and the garnet. So this is not a good thing. And we found that we could eliminate that by growing the platinum directly on top of the garnet in the chamber. And this in situ growth is accomplished by adding a sputter gun inside the PLD chamber. And this has some quite dramatic consequences. For example, if we compare the platinum deposited ex situ, which has the contamination, then when we measure the density of the material as a function of depth, we see this dip, which is due to carbon-rich layer at the interface between the platinum and the garnet. If we avoid that by growing the platinum in situ, there's no dip. And in fact, now if we measure the magnetization versus depth, we see quite a lot of magnetism in the platinum itself, even though platinum is not a magnetic metal. And this is a proximity-induced magnetism, which is caused by the intimate contact between the platinum and the garnet. And it actually scales with the net moment of the garnet. So as we go through compensation, the proximity magnetism in the platinum vanishes. And then as we go away from compensation, it comes back again. So this coupling is actually very different from the proximity magnetism in, say, metal-metal systems like rare earth transition metal alloys with platinum on top. And it's a pretty interesting phenomenon. But clearly the platinum is interacting with the net magnetization of the garnet and not just with one of the sublattices. Okay, so we've grown plenty of good quality garnet on garnet substrates. Now, how about growing it onto a useful substrate like silicon? It turns out that one can grow garnet on silicon, and it comes out to be polycrystalline. This AFM image at the top, if you look carefully, you can see these are the grain boundaries, these straight lines, and each grain has a radiating pattern, which is due to the nucleation and growth process. So what happens during growth is that as we deposit the material, it's amorphous. And then when we do a later on rapid thermal anneal, the garnet crystallizes quite quickly. And in the case of this dysprosium garnet, it was annealed for 3 minutes at 850 degrees C, and it comes out as perfect single phase garnet. Although polycrystalline, each of those grains is rather big and they're quite perfect. So we can make polycrystalline garnets, but this temperature is very high for a back-end device process, and we'd like to lower the temperature. And we found we could do that by adding bismuth into the garnet. So if you look here at this table, the different rows represent different compositions of garnet. So the top row is terbium garnet, and it needs 800 or 900 degrees to crystallize it. As you can see here from the X-ray trace, we don't get crystallization at 700 C, we only get it at 800 or 900. If we look down here at terbium 0.6, bismuth 0.4, then this one will crystallize at 600 or 700 degrees C, as you can see from the X-ray trace here. And moreover, this material has a low coercivity and actually a pretty favorable magneto-optical behavior. So it does look that one can get garnet films to grow on silicon or other non-garnet substrates by choosing the composition and finding one that crystallizes relatively easily. Okay, so that's a background to the engineering of these films. Now I want to show you some spintronic results on how we can use electrical signals in a platinum layer to both read and write the magnetization of a garnet layer. We make Hall crosses where we measure the Hall resistance in the platinum as we flow a current through the platinum. And I remind you that the garnet itself is a very good insulator, so none of this charge current is passing through the garnet. It's all in the platinum. Nonetheless, we measure a Hall resistance, and there's an anomalous Hall effect, which corresponds to the switching of the garnet. So there's a communication between the platinum and the thulium garnet. And what's happening is that a spin current from the platinum is going down into the thulium garnet, interacting with the magnetization of the thulium garnet, and then being reflected back into the platinum. And that's what we can detect here as this anomalous Hall effect signal. So the signal depends on the angle of the magnetization, M, here, of the thulium garnet. And we can use that to detect the magnetization and measure properties like the anisotropy. We also find that we can switch the magnetization, and that's the most exciting part. One comment before I go to that is that we can use this to track down the nature of the interaction between that spin current and the garnet. And if we go back and measure these kind of anomalous Hall behavior of terbium garnet with different scandium substitutions, we can find out that the interaction between the spin current and the garnet actually really only depends on the ion. It doesn't depend very much on the rare earth. So we can put different rare earths in there and we can get the same kind of behavior. All of them actually behave rather similarly. Okay, so back to our switching. We have a more controlled experiment where we can introduce a domain wall into a track of garnet. So horizontally in this device is a track of garnet with a platinum layer on top of it. And then overlaid on that is a gold nucleation wire. So first of all, a pulse through the gold wire will nucleate a domain wall in the garnet from the Ørsted field of the current. And then that domain wall can be pushed along by flowing a current through the platinum layer. And this is a spin orbit torque switching. What's happening again is that the spin current from the platinum is going into the garnet, but now instead of just reading the garnet, we're actually pushing that domain wall along with the torque from the spin current that's coming from the platinum. And we can measure the velocity of that domain wall. And you can see it here in these MOC images. The purple and grayish color are the up and down magnetizations, and the domain wall moved from here at time 0 up to here at, say, 58 nanoseconds or 35. You can see it propagating, and we can measure its velocity. So first of all, why are those domain walls moving at all? It turns out that from the symmetry of the spin-orbit torque effect, the domain wall must be a Néel domain wall with its magnetization lying in plane like this, parallel to the current. It can't be a block wall, because those block walls are immune to the spin-orbit torque effect, which means that we don't expect to see the domain wall moving. So this is proving that the domain wall has a Néel character, and all the domain walls move the same way, which means that they're homochiral. They're all left-handed or they're all right-handed. In fact, here they're all left-handed. And that means that there must be a DMI, a Dzyaloshinskii-Moriya interaction between the garnet and the substrate, in fact, which is making all the domain walls left-handed Néel domain walls. And if we apply an in-plane field to convert the Néel domain wall into a block domain wall, then it stops moving, and we can use that to measure the strength of the DMI, which is about 50 Oersteds in this particular experiment. So with that in mind, we can understand now how to control the switching behavior or the speed of the domain wall. If we measure for thulium garnet, the domain wall velocity as a function of the current density in the platinum, when the garnet is thick, the domain wall doesn't move very fast. But as it gets thinner, and this is down to 2.4 nanometers, which is 2 unit cells, the domain wall moves very fast. It gets up to about 1500 meters per second. And if we give it some help with an in-plane field, we can get it up to 2 kilometers per second. And the thickness dependence of this behavior gives us an interfacial DMI, and we can measure the coefficient, the DMI coefficient. So it's not very big, but it's big enough to give us fast domain wall motion without requiring any kind of applied field. So a purely current-driven domain wall motion. So this 2 kilometers per second is quite fast. But if we move on and look at a different garnet, this is bismuth-Yig, we can get up to 4 kilometers per second, 4.3 kilometers per second here for this bismuth garnet. And it turns out that we do need an in-plane field, which means that for the bismuth-Yig, there's no DMI stabilizing chiral domain walls. The domain walls need to be made to be left-handed Néel walls by applying an in-plane field. And this is telling us something about the DMI. We only get DMI in rare earth garnet films, not in bismuth-Yig, which doesn't have any rare earths in it. But because bismuth-Yig has a very low damping, we can get extremely fast domain wall motion. And in fact, this is a relativistic speed because it's approaching the Magnon group velocity, which is about 5 kilometers per second in this material. So it's analogous to moving something close to the speed of light. The Magnon group velocity is the fastest possible velocity that these spin textures could actually move at. And we can drive it almost that fast with this spin orbit torque. Okay, so what we'd really like to do is combine the benefits of both these materials. We'd like to have some DMI, but we'd also like to have very low damping, which allows for the very high velocities. And the bismuth-Yig has low damping, but it lacks DMI. The rare earth garnets have DMI, but they have a much higher damping because rare earths tend to cause a lot of damping. So by taking a mixture of the two, bilayers or co-depositions of bismuth and thulium garnets, we can get both a reasonable DMI and a reasonable damping. And in that sense, we can now get spin-orbit torque switching of domain walls in bismuth-thulium garnet without requiring an in-plane field. And this is some very recent data showing a domain in a Hall cross in bismuth-thulium garnet and its motion under an applied current without any applied field. One last thing about spintronics in bismuth-Yig or garnets in general. I've talked about using spin orbit torques to switch the magnetization by moving domain walls. We can also use spin waves themselves. And in these experiments, we're taking a track that's running top to bottom out of bismuth garnet, and we've put a couple of antennas on it. There's no platinum anywhere. We've just got gold antennas on top of a bare bismuth garnet film. And if we place a domain wall in between these antennas, actually near one of the antennas, and we put a pulse of RF power into the antenna, it will actually push the domain wall along, and you can see it down here. One of them's moved down to here. And the spin wave, which is injected by the antenna, is actually interacting with the domain wall and pushing it along. So we have a magnon domain wall interaction. And the spin wave, or magnon, occurs at about 4 gigahertz in this particular material. And that resonant frequency, there's a good coupling between the signal in the antenna and the spin wave generation in the garnet, and that allows for an efficient transfer of energy, or a more efficient, I should say. If we run off resonance, then we don't see any of these effects taking place. So this gives us another avenue to explore in terms of electrical excitation of magnetism in these kinds of materials. Okay, so I've talked about spintronics. I now want to talk about photonics, integrated photonics. And what has motivated our work in integrated photonics is a rather long-standing problem, which is that in a photonic circuit, you have lasers which generate light, you have a detector which picks up the light, and in between you have various things going on. There's a signal that's modulated, for example. But how do we make sure all the light is flowing in the right way? We have isolators, which are optical diodes that allow light to go in one direction, but block light going in the other direction. And this component is essential for photonic integrated circuit. So if we imagine a photonic IC, we can have all these functions, the laser, the modulator, the detector, all built on a semiconductor platform. But the diode has been a challenge. And it turns out that these diodes in bulk are made using garnets. They're magneto-optical devices, and they work because the material is transparent, and when polarized light travels through it, that polarization is rotated. So in this case, we have up-down polarization. The light goes through the piece of magneto-optical material. There's a magnetic field that's keeping it magnetized, and the light is rotated, let's say by 45 degrees. If we now imagine light going back the other way, that light is rotated by another 45 degrees, and it ends up at 90 degrees. So the two paths through the garnet or magneto-optical material are not equivalent. This is called non-reciprocity. So we want to have a material with a good figure of merit. That means we want a big Faraday rotation and a small optical absorption. So we're going to classify these materials according to their figure of merit, which is Faraday rotation divided by absorption. So this problem has been solved in bulk. These are all commercial isolators. You can buy one, and it works fine, but it's very difficult to produce that on a chip. And we've been interested in solving that problem. So our first job was to identify good materials. And it turns out that YIG itself is not particularly good, but adding cerium or bismuth to it makes for a very good magneto-optical performance, a good figure of merit. So we have to develop methods of growing those films on silicon. And we can use a seed layer of YIG on top of the cerium YIG, as it turns out, or underneath it. Or some of the garnets will grow by themselves. So let's look at some of their performance. First of all, bismuth YIG. As we add bismuth, we improve the magneto-optical property, but the material gets harder and harder to crystallize. So there's a limit on how much one can put in. And we can get quite good figures of merit of these polycrystalline materials, 600 or 400 degrees per decibel, which is actually a pretty good number for an integrated photonic device. And then in some recent work we just published, we found that by using bismuth terbium garnet, we could get even better numbers. So these polycrystalline materials have very good performance. Let's look at how we can put them into a device. If we have, we can't use the kind of bulk style of isolator because it actually does not work in a thin film geometry. So we have to do something different, and we use these resonant devices like a ring resonator. Light is traveling along a waveguide, and we put a ring resonator adjacent to the waveguide. We want the forward light to be not resonant with the isolator, so it's not actually interacting with the resonator, and it just passes through. So forward light just goes through, but backward light, we need to absorb that, and it gets picked up on the ring. It goes around the ring, and eventually it gets lost. How can this ring have a different resonance for clockwise and for anti-clockwise light? Well, that's because we've put a magneto-optical material on top of it, and we've magnetized it sideways, and that gives us a non-reciprocal phase shift. So that's the basis for making these kind of isolators. So we can make actually a couple of different devices. We can make the racetrack device I just described, this ring resonator. We can also make a Mach-Zehnder device, an interferometer, where the incoming light is split into two halves, and they both experience opposite non-reciprocal phase shifts. And then when they get to the output, they add up. But when you go the other way, the two sides become out of phase and they cancel. So both of these devices, the ring resonator and the Mach-Zehnder, have pros and cons, but the Mach-Zehnder in particular is advantageous because it has a very wide bandwidth of operation. We can model the propagation of light through the silicon waveguide with the cladding of garnet, cerium yig, or bismuth yig, whichever one it happens to be, or bismuth terbium garnet. And I want to point out that there are actually two modes for this. The TM mode, transverse magnetic mode, where the garnet needs to be on top of the waveguide, and then the TE mode, transverse electric mode, where the garnet needs to be on the side of the waveguide. And this one is much more difficult to implement, but it's actually the one you want because on-chip lasers produce TE mode of light. So we can design some devices, and this is the best one ever that we've made. This particular ring resonator has a loss of only 3 dB and a 40 dB isolation ratio. But as you can see, it has a very narrow bandwidth. So it only works well at a very specific wavelength. So to improve that, we can use the Mach-Zehnder. It has slightly less favorable performance in terms of isolation ratio. This one has about 30 dB isolation ratio, but it has a much wider bandwidth, so you can use it for a range of different wavelengths. And you can see here, the garnet is grown on top of the silicon waveguide. Now, these are both TM mode devices, and we can make the TE mode by putting the garnet on the sidewall. You can see it there. And these are less high in terms of isolation ratio, but they work for the TE mode of light. So this is a ring resonator, and this one here is a Mach-Zehnder for TE mode of light. So this problem is soluble in terms of developing devices, but there's still a lot of challenges in growing this material with good quality on the top or the side wall of these silicon waveguides and crystallizing it. Okay, so the last thing I'm going to talk about, maybe I should find out, Professor Wang, how long have I got?
I think you can go as long as you want.
Well, I'm sure the audience doesn't.
You are the one in the late night, so. Okay,
well, let's just do a five or so more minutes on this, and then we can go for questions. I want to show you some results on on oxides or insulators other than garnets. And we're focusing on making perovskite and spinel materials, which show both magnetism and ferroelectricity. So the garnets are wonderful magnets, but they're not ferroelectric. And we have many devices where we would like to take advantage of ferroelectric coupling to the magnetism. So one example of this is a device concept called MESO, which is developed by Intel. And there are others of these kinds of devices, but I'm just highlighting this one. In these kinds of devices, we have an input signal, which is a voltage or a charge. We convert it into a magnetic signal by using some kind of magnetoelectric effect, which is a coupling between, say, a voltage and magnetic or magnetization of the material. That magnetic charge is manipulated or stored or combined, whatever you want to do with it. And when you want to read back, you need to convert it back into a charge using some sort of effect like what we've been talking about before, read back using an inverse spin Hall effect, for example. And then we can finally take that, that signal out of the device and feed it into the next device. So what we need are these coupling effects between charge and magnetism. And that's where all the motivation is to study magnetoelectric performance, magnetoelectric properties. So I want to talk about two things. One of them is perovskites, which are very well known as ferroelectric materials, but they're not so well known as magnetic materials. And then I want to talk about two-phase materials, which consist of both a perovskite and a spinel, which provide respectively ferroelectricity and magnetism. So one thing that we have been working on is how to create magnetism and ferroelectricity together in one material. And the classic material that shows both a magnetic order and a ferroelectric order is bismuth ferrite, BiFeO3, which is a perovskite structure. If we replace that bismuth with something else, in this case yttrium, then in bulk, that YFO, which is called yttrium orthoferrite, is a centrosymmetric material, and it shouldn't be ferroelectric at all. It's actually a canted antiferromagnet. So it has a little bit of magnetism, but no ferroelectricity. And we found rather accidentally that when we grew thin films of this material, it turned out to be a ferroelectric, quite a good one. So we can see here, we have a bit of magnetism, not very much, but there's some there. But here we've got some ferroelectricity. This is a PE loop, polarization versus electric field. And this is a scanning force measurement called PFM, piezo response force microscopy. And you can see here again, this is a ferroelectric response. So what's going on here? How can something that is a centrosymmetric orthorhombic material in bulk show this amount of ferroelectricity? And we tracked it down to antisite defects. So if you look at this microscopy, there's some extra yttrium right here where the white arrows are. These are antisite defects of yttrium sitting on the ion sites. And if we go along and measure the behavior of this material as a function of composition, when there's an iron-rich composition, we get no ferroelectricity. And you can see that in these two cases. But when there's an excess of yttrium, we get a ferroelectric response. You can see here and here. So here the yttrium to iron is 1.03, and here it's 1.11. And even up to 1.2, we get ferroelectric behavior. So where did that come from? And this is stable at room temperature, in fact, well above room temperature. And we found that it comes from antisite defects. So the excess yttrium is sitting in the iron site. So iron is gold color, and the yttrium is the blue. And when the yttrium sits in the iron site, it actually causes a distortion which is no longer centrosymmetric. So it goes from this space group PBNM to a space group R3C, which is non-centrosymmetric. And so this non-centrosymmetric structure gives us the polarization. And we measured it for yttrium, but DFT predicts it should be stronger even for smaller rare earths like lutetium and ytterbium. So we are currently looking at those. And this gives us a wider option for multiferroics. Another way of getting multiferroic behavior is to combine a ferroelectric material and a magnetic material. For example, a ferroelectric perovskite like bismuth ferrite and a spinel ferrite, which is magnetic like cobalt ferrite. And we've worked on these for some years. We can co-deposit them, and these two materials are immiscible, so you get pillars of the magnetic phase embedded in a matrix of the ferroelectric phase. And we can even template the positions of those features to get an ordered arrangement of single domain magnetic particles embedded in a ferroelectric matrix. We tried this out with YFO, our new ferroelectric material, and it turned out it did make these kind of composite structures with cobalt ferrite. And they even have both substantial magnetism, which is coming from the cobalt ferrite, and substantial ferroelectricity coming from the YFO. And these, in fact, are multiferroic, because if we apply a magnetic field, we can influence the ferroelectric response. And although we haven't measured it, I would expect that if we apply an electric field, we can influence the magnetic response. And those couplings are due to strain transfer between the two phases, which means that they're coupled to each other. I want to wrap up with one more comment about electrical control of magnetism. Some of the materials we looked at, like this one, strontium cobalt ferrite, strontium, the cobalt and iron are in the B sites of the perovskite. They can be manipulated by ionic liquid gating, and they can be changed between two different crystal structures, brown millerite and perovskite. And this is done by removing or inserting oxygen. So if we start with as grown material, which is brown millerite, that has a composition of strontium cobalt iron O2.5, if we add oxygen to it, we can turn it into a perovskite, SCFO3, and we can turn its magnetism on. So as we go back and forth, we can go from as grown non-magnetic to a magnetic phase, and then back to a non-magnetic phase. And this is actually due to changes in the valence states of the cobalt and iron as we add and subtract oxygen from the structure. So this is a quite robust room temperature method for imposing an electrical control on the magnetism of an insulating material. So I'm going to stop there and thank you for your patience. I hope I've shown you some interesting properties of complex oxides and ways of manipulating their properties to get desirable magnetic, ferroelectric and magnetoelectric responses. So garnets are good insulators, typically low damping, and they have tunable properties which we can manipulate. We can get very fast domain wall motion in these garnets, approaching the theoretical limit of the Magnon group velocity. We get useful figures of merit in magneto-optical response, which means we can use them in optical devices for photonics, integrated photonics. And I've shown you some new mechanisms for ferroelectricity and for multiferroic control of magnetism using electric signals, and hopefully ferroelectricity using a magnetic signal. So our challenges for devices are still to control the thermal budget and to grow the phase that we want on a potentially non-favorable substrate. But beyond that, these materials are just offering a huge range of additional properties which can make for very interesting devices going forwards. So thank you very much.
Hey, Prof. Rose, thank you very much. I think we do have time for some questions. Maybe first I ask one or two questions, simple questions to let the audience to prepare. For the audience, if you are a bit shy, you can also type your questions in the chat window. Maybe I have, my first question would be, I think in your slide number 17, you had the data about magnetization versus depth. So how did you do that?
Oh, those are measured using polarized neutron reflectometry. Let me go back to that to remind people what it was. So you use a beam of polarized neutrons. It is, there we go. It gives you a depth profile of three things: the density of the material, the absorption of the neutrons, and the magnetization of the neutrons. And you get that by modeling. You measure it for different polarizations of neutrons. So it has to be done in a beamline. And the fitting is quite complex because there are a lot of variables, but we basically know the thickness of our layers and what the layers are made of. And so we can iteratively improve the fit and back out the magnetization as a function of depth.
Does it require a huge sample?
No, it's a few millimeters square. Most of our samples are 5 to 10 millimeters across.
I see. Okay. The second question is about the ionic liquid gating on strontium cobalt iron oxide. You have shown that you can turn the magnetization on and off. My question is, are you able to, let's say, stabilize the magnetization at intermediate state, like get multiple state magnetization? Yeah.
You can do. The question is, what's the mechanism for this? Because the as-grown one is the brown millerite. It is oxygen deficient. If we gate it, we can get it towards strontium cobalt iron O3. But when it's O3, the cobalt and iron would all be in 4+ valence states, and that's a very unfavorable valence state. So even the Perovskite structure is still oxygen deficient to some extent. So this is a rather continuous behavior. The Perovskite can tolerate quite a lot of range of oxygen content, but if you go down to 2.5, it converts into the brown millerite structure. So within the Perovskite range, we can actually get a range of different amounts of magnetization.
I see. Okay. For the audience, if you have questions, feel free to ask. You can turn on your mic if you want. Let's see whether someone is going to ask a question. Maybe they are a bit shy.
Don't be shy, guys.
You can ask any question. Yeah, just ask any question. It can be very simple or fundamental or technical questions. If no, then I assume that's because your talk is really excellent. Everyone knows it very well.
Well, I hope so. I hope rather than totally incomprehensible, but there you go.
Okay. Looks like no other questions. Okay, then probably in consideration of the time, then we can stop here. And if you have more questions, you can feel free to contact Prof. Rose.
Yes, please do email me and anyone if you have any questions or comments or follow-ups. I'll be happy to respond.
Okay, great. Now I think the seminar will close now, and thank you very much again for the talk. And we look forward to meeting you in person.
And thanks everyone for listening.
Yeah.
Okay.
Have a good night.
Have a good morning. Bye everyone.
Yeah.